Okay, so we'll be having an additional problems on axial deformation. So let us consider this problem number 3. So for problem number 3, this weight is supported by two bars. We have aluminum and steel. Those lengths were given, as well as the modulus of elasticity, as well as the diameter. So we are going to determine the vertical movement of W if its magnitude is 50 kilonewton. The weight is supported by aluminum and steel rods as shown. So practically, number 1, we should initially illustrate the free body diagram of this one. And as we all know, we can right away determine the axial forces on these bars, aluminum and steel. So let us do that now. We have 50 kilonewton here. So summation moments at B to solve for aluminum, and summation moments at A to solve for the axial load at the steel bar. Okay, so that is the first step. So remember that we should assure or ensure these forces by summation forces vertical. So if we perform the summation moments at A, we yield at 35,000 Newton here. And then for aluminum, we have also 15,000. We add that one, we have going upwards 35,000 plus 15,000, that is 50,000, which is equivalent to downward force weight. So that is our check mechanism in this problem. So next is we can now determine the deformation of each bar. So we compute for the deformation of each of the rods. For aluminum, again we apply this formula, PL over AE of aluminum. We substitute. We have 15,000 times 3,500. We have a circular cross section, 25 in diameter, and 70,000 for its modulus of elasticity. So by this we have 1.53 millimeter. Similarly, we are going to do that to the steel. Therefore, we have here 2.51 millimeter for deformation of steel. So as we can see, we have a greater value for the deformation of steel comparing to the delta of aluminum. So we can illustrate that in our figure. So illustrating the elastic deformation geometry, this is the stretch of aluminum as well as the stretch of the steel. Okay, so the stretch of steel is greater than of that of delta of aluminum. So we can form here a right triangle. Just bisect this right triangle to form the right triangle here from the trapezoidal shape. Okay, so the purpose of that is, of course, we will relate this delta through similar triangles. Okay, by similar triangles, of course, we should know first the dimension, the inner dimension of this right triangle. So for this one, we have delta due to weight minus delta aluminum. This is the dimension. Okay, and for this one, the steel deformation less delta aluminum is this dimension. Now that we have these dimensions by similar triangles, we have delta due to weight minus delta aluminum all over 3.5 is equal to delta steel minus delta aluminum divided by 5. So by cross multiplication and by manipulation, we can now get the value of delta on W. Okay, the delta of W. Okay, so that is equal to 2.21 millimeter. Okay, so let us consider this problem here. We have the three rigid bars A, B, and CD, or the two rigid bars A, B, and CD shown are supported by pins at A and pins at C, and by these two rods. So A, B, and CD here is connected by steel rod, and then is also supported at the upper bar by a suspended aluminum bar. So all of the properties are given here. We are going now to determine the maximum force which can be applied if its vertical movement is limited to 5 millimeter. So what is the meaning of this? We are going to determine the value of P here in order to limit our vertical movement 5 mm. So where's that 5 mm? So if we are going to illustrate that one, the vertical movement is measured from the point P. So whatever the displacement of this point P, we should limit it to 5 millimeter. Okay, so it is just limited to 5 millimeter displacement at this. So to do this, we'll just gonna employ the formula of delta is equal to PL over AE. So what member are subjected to this PL over AE? On the figure, this AB is locked or restrained at the position A. It will only be rotating clockwise or counterclockwise. So this, in this case, it will rotate downwards or clockwise. Okay, same true with CD because it is free to swing at point C. Okay, when we detach these bars. Now the force is going downwards, so it is obvious that aluminum and steel will be stretched. Okay, will be stretched. So whenever there will be a stretch on aluminum and steel, again we are going to limit the displacement at P. So the first step to apply this formula is, of course, to get the forces out of the free body diagram. Okay, so out of the free body diagram, so let us illustrate now our free body diagram. Okay, so considering here AB, say we have AB having a reaction of a vertical and horizontal reaction, and obviously this has no value because there is no any horizontal force here. And then for the next, of course, we will be having a tensile force by the aluminum. So for steel, of course, there will be also a tensile for steel. Okay, so when we say tensile, it is an arrow or a force arrow having a direction away from the joint. So see, this is P of aluminum and this is P for steel. So let us also label this RA vertical and this is RA horizontal. So we further draw our FBD for CD. This is bar CD. So on this bar again, action and reaction, this is oppositely directed but the same magnitude because it will just transmit to our bar CD. So this is P of steel, and this is our value for P. So this has reaction as well. We have RC horizontal and a vertical reaction at C. Okay, so obviously we're gonna take moments at this point for that CD. Sorry, this is AB, and this is bar CD. So we're going to take moments at A. We have, of course, we should have a distance here. I think this is 3 meters, 3 meters, 3 meters, and this is also 3 meters. So let us indicate those distances here also. Okay, so aluminum will have a negative rotation or counterclockwise rotation. That is PAL times 3. So we indicate the direction by negative sign. The direction of rotation is counterclockwise, plus P of steel times the moment arm from A is 6. Now this is equal to 0. So let us delegate this as equation 1. And then for FBD of CD, we will take moments at C. Okay. We have P is clockwise times 3 minus P of steel times 6. This is equal to 0. So let this be our equation 2. So we can now relate and manipulate by manipulation of the equation both in terms of P. Okay. So from equation 1, we can say that P of steel is equal to, we transpose that to the other side, 3PAL. Okay, divided by 6. So 6 came from a variable adjacent to PST. Okay, we'll just cross multiply that one. So therefore, P of steel is equal to 0.5 of P of aluminum. And then further, we can also see that P of steel is equal to, we transpose this becomes negative, so negative will just cancel on both sides. We have 3P over 6, 3P all over 6. So in short, P of steel is also equal to 0.5 of P of steel, sorry, so P of steel transpose that to the 3P over 6 is 0.5 of P. P of steel is equal to 0.5 of P. So equating P of steel is equal to P of steel we have now 0.5 of P of aluminum is equal to 0.5 of P as well. Therefore, this is just cancelled. We can say that P is equal to P of aluminum. So P is in terms of aluminum, and P of steel will also be in terms of P. So both in terms of P. So our purpose here is we are going to substitute all of the values all in terms of a single unknown, that is P. So that is the purpose here actually. So let us name this as equation 3 and this as equation 4. Now, we now relate the deformation, okay, so that we can utilize these forces. So what about the deformation? So let us have the illustration here. If this is AB and this is our CD, okay, A, B, C, and D. So you imagine what will be the scenario. If I'm going to pull this down, let us assume that all of the bars is still on rigid, okay? All of the bars, or assume that all bars is not subjected to any elongation or does not yield. So that is the first assumption. So if it does not yield, remember this is connected, okay? That is connected, and this is also connected to the ceiling. Now if I'm going to pull this down, apply the P here, having this to be rigid, so it will not elongate, okay? Of course, D will transfer to a certain point here, say D prime, right? So if I'm going to label this as delta, say this is delta B. So I label that as delta B because whatever the deformation here, D to D prime, is also equal to what? The displacement from B to B prime, okay? B to B prime. See, this is also delta B. Alright? So, let us illustrate the final position of that one. We have here a triangle. Okay? So, again, delta B is also delta B here because assuming that this bar, what is that bar? Steel bar. Okay, steel bar. Assuming that the steel bar is rigid or is not subject to any deformation or elongation. If you are going to pull this down, of course it will remain at C. It will come down. So whatever the vertical displacement here is also the displacement here. Okay, that is why if this is delta B, this is also delta B. So that's it. But having that deformation assumed to be rigid, or the steel bar assumed to be rigid, we will now take into consideration the stretch also of the steel bar. So therefore, this will not be the final position of D. It will further go down because of the stretch or the elongation caused by the steel. Okay, say another point here, say D double prime. Say we are going to label that as delta steel. Okay, and then for this one, obviously this is delta on aluminum. So we now project the final position of the final position of okay, of CD. So this is the final position of CD. Okay, so actually we have a right triangle. So there will be ABD prime, ABB prime triangle and ACDD double prime triangle there. So working with the triangles, okay, let us now label all the delta here. Say this is delta aluminum. Say this delta is the vertical displacement we are talking about. It is limited to 5 millimeters. So complete dimension and complete variables. Let us have ratio and proportion. By ratio and proportion, we have delta aluminum is to 3 plus equals delta B is to 6, and we come up with an equation. Delta B is equal to 6 over 3 of aluminum, that is 2 delta aluminum. So this is for triangle, a triangle ABB prime, ABB prime, and then a triangle CDD prime. We have five is to 3, right? This is equal to delta B plus delta steel is to 6. Okay, so simplifying further, 5 times 6 is 30 divided by 3, that is 10. 10 is equal to delta B plus delta steel, and here we substitute the value. Say 10 is equal to 2 delta aluminum plus delta steel. So all in terms of aluminum and steel, we now substitute. So 2, this is PL all over AE of aluminum plus PL over AE of steel, okay. So this is 10 is equal to 2. What is P of aluminum equal to? In terms of P, we have P aluminum is equal to P is equal to P. P aluminum is equal to P. So you just place there the P. What is the length of the aluminum? What was the length of the aluminum? Length of aluminum is 2 meters, and steel as well is 2 meters. Two meters, area 500, E is 70, L is 2 meters, 300, and 200,000 megapascal. Okay, so L here is 2000. Alright, and the area for aluminum area is 500. And this is 70 gigapascal or 70,000 megapascals. Plus, what is P of steel here? The P of steel is 0.5 of P from equation 3. Okay, so we just place that here, 0.5 of P times, this is also 2000, and the area is 300. This is 200,000 for Young's modulus of elasticity. So finally, we can get the value of P. So we have 76,363 Newton. So this is the answer for that problem.